All right, we are recording now. How's everyone doing? Did you have a good long weekend? Good. So did I. My parents are down visiting from Canada over the Thanksgiving holiday, so that's been nice. You should have all by now gotten back your grade on the exam, and I'm quite happy to answer questions if there's something that you're not sure about. If something comes up frequently enough, I'll send out an announcement about it. But I tried to make fairly descriptive comments on, at least on the hand-graded ones, about why there were points taken off in some cases. Overall, the exam was not bad, not great. It was certainly, on average, lower than the first exam, and there was some apparent confusion about hypothesis testing and a bit of difficulty with performing them. So that was why I decided to make a makeup exam available if you want to take it. So, but you should all now be started on your final projects. The first section, your introduction, you were supposed to post a draft to your discussion group by the end of the day today. And then before the next section is completed, so next Monday, I would like you to provide some feedback on your peers. If there's it, so I am not able to go through and review all of them at every stage, but again, if there's anything where you would like me to intervene or provide some additional feedback, just point me, especially send me a link to the discussion where it's going on, and I will take a look and weigh in. The idea being, A, so that you're not doing the entire project the day before your final presentations, and B, so that you get some idea of what other people are doing and get some peer feedback on the way, which in my experience is pretty good because most people hand in pretty good final presentations. So please do make sure that you get something posted by tonight, and then before next Monday that you have provided some kind of feedback to everyone who has posted something in your group. And since for most of the part, we have this 10% participation grade, I don't require in-class attendance. I don't require you to be asking questions throughout classes or anything like that. This is the part where I do require you to do something, participating in the class through submitting your draft materials and providing feedback. So this section and what you post in your Google group is what I'll base that 10% on. So don't be surprised when you get to the end. I am going to look through. Blackboard provides very convenient ways for every student for me to take a look and see what you have posted, and that's what I'm going to base your participation grade on. So no surprises, just it's easy. You just have to post your draft stuff and provide some feedback on what other people in your group do, and you will get full 10 out of 10 participation points. That's it. Yes?
I have a question about the project. So at the end of the day, we'll be presenting a poster. So it's also said in the email that we can provide the weekly task in bullet points. Is that my understanding?
So generally, your posters are done in bullet points.
Correct.
And yeah, you don't have to, in the end, it's going to be like a poster. The most convenient way to do it is probably to do it on letter-sized paper and print, so you can use a regular printer, and I'll give you poster board that you can post those up on. So, for Blackboard, the most convenient way to do it is not in your Word document or something, but directly into the post in Blackboard, just because then you can read it directly without having to open up the file. I mean, it doesn't really matter, but that's,
right. So each week we don't have to. My bottom line question is, it doesn't have to be submitted in like a paragraph formation or something like that. Okay.
No, think about
how it's going to be.
Yeah, so the way a poster presentation goes is there's going to be, you know, an easel with your board and your things. We're going to take turns. You'll have your turn where everyone, myself and Tony and your classmates included, will come up and watch while you give like a 3-minute presentation on your poster. You'll point to things on your poster. Nobody has time to read 10 pages worth of text during that time, so it's just going to be bullet points and tables and figures, so that you can present it. It's not a written report; it's a poster presentation.
Okay.
Yeah.
Thank you.
You're welcome. I also can, so I forget the date of the presentations, I think it's December 19th, but I can also allow some people, if you want, to present the week before that as well. So if you would like to present a week earlier, just let me know. And if there's anyone opting to do that, then I'll bring some poster boards the week before and let you go early. Any other questions about final project or about the exam or the makeup exam before I get started on lecture? Yes?
For the exams, I was not able to see my feedback.
Under your grades, you have to click, your actual grade is hyperlinked and you have to click on it. I can post some instructions for how to do it, but I know it is possible. Just like everything in Blackboard, it's totally unintuitive. You just, yeah, you have to either trial and error or Google it.
Just click your grade. Yeah. I also didn't know how to do it.
Yeah.
Oh.
All right. So we're moving on to a new kind of data analysis and hypothesis testing for categorical and binary variables. So I'm going to introduce a few data analysis methods for categorical variables, the chi-squared test for frequency tables. I'll introduce relative risk and odds ratio and give a few alternatives to the chi-squared test. This is all from chapter 3 in the textbook. I found this interesting example, and I posted the paper behind this data set in Blackboard with today's lecture. So it's a pretty interesting article, and I'd recommend taking a look at it. And it gets into this analysis in a lot more detail than I do, but it's a very accessible paper. It's not statistically daunting or anything, but it talks about this analysis quite a bit, which was a classification of court trials where individuals were convicted of homicides in Florida but over about a decade. And it asked the question of whether there was evidence of discrimination in the death penalty verdict. And for each of these cases, they were categorized first by the race of the defendant, which was just categorized as black or white, and then by whether that in this guilty verdict, whether the sentencing resulted in death penalty or not. And they made this 2x2 table and asked the question, is there evidence of discrimination in the death penalty verdict? Or put another way, is the death penalty verdict independent of the race of the defendant? Which provides a nice motivation for what we're going to do today, which is first introducing a hypothesis test that will allow us to test for that independence, because of course we expect, like every other kind of sampling we do, there's a certain amount of sampling variation, and we cannot make a generalized statement about the relationship between two variables without accounting for that fact that there is sampling variation in any incomplete set of data that we have. So what is this hypothesis test? You're all pretty familiar now with null and alternative hypotheses, even if many of you are still a little bit confused about it. Good news is we'll be talking about it more. The hypotheses are a little bit different in this test, but the idea is the same. So I'm going to write down a null hypothesis here, just in words, that the death penalty verdict and the race of the defendant are independent, with the alternative hypothesis that they are not independent. So just to point out some properties of this null hypothesis, one is that these are statements about populations. I'm not saying the death penalty verdict during these 11 years or for the observed defendants. I'm making a more general statement about that includes people who we haven't observed. So I'm treating these 11 years worth of data that we have as a sample that is supposed to be representative of of future years, of past years, a more general population. Written equivalently here is in terms of population proportions, that the proportion of death penalties for white defendants is equal to that for black defendants, with the alternative hypothesis that just that they are not equal. And a lot of people lost some grades on the exam for writing something like this, or there's the one about New Yorkers being evenly divided in their support of a program. But this way it is written really implies two samples, and that was a one sample test, and it was a test that one proportion was equal to 50% or 0.5, which is why something like this didn't get full grades. This is a case where both of these are subject to sampling error. Yes?
That is equal to the null hypothesis. I read it as the proportion of white people in the death and equal to the proportion of white people in the not death.
No, it's not the same as that. So what the question was, is this equivalent to saying that the proportion of death penalties among white people equal to the proportion of non-death penalties among white people? That would be more like what the exam question was is that proportion equal to 50%? Whereas the proportion can be anything here. It's just that the proportion is the same for black and for white defendants. And the exception that I took with writing there that the proportion in favor is equal to the proportion not in favor is that then looks like two separate population parameters, where there's only one population parameter there with a null hypothesis that is equal to 50%. So it would be possible to take a proportions approach here, like you have done already, and make a normal approximation for the sampling distributions of the proportions, which would actually work pretty well here because we have a very large sample size, and then perform a two-sample z-test or construct a confidence interval and use methods that you've learned already. But in this case, it's actually better to take this new approach I'm going to teach you using the contingency table and a chi-squared test. And the reason is that we don't have to make any of those same, we don't have to make the same approximations. And there are additional alternatives for analyzing the frequency table. The idea is first, okay, assuming that the null hypothesis is true and race and the death penalty are independent, then what counts would we expect to see given the number of people of each race and the number of the number of death, or the proportions of death penalty assigned. If they're truly independent, then what counts would we expect to see? And if the counts that we observe are different enough from what we expect, then we're probably going to reject that null hypothesis. If they're fairly close, you don't have to be exactly the same, but if they're fairly close, then we will have to accept the null hypothesis. What does that table look like of expected counts? Well, you can start filling it in. You start with the margins. So we have the number of black and white defendants, which is about even here, close to 5,000 each. And we have the number who received the death penalty and who did not. And the large majority did not. So how would we fill this corner in? Well, if they're independent, we can just take, let's say, this fraction, 364 over 10,000, or sorry, over 10,068, and multiply it by 4909 to give us this top left corner. And you could just do that for each corner. Just take the proportion from the columns times the sum for the row, and that gives you the entry. So for example, here 4909 times 364 over 10,068 gives you about 177.5. So that's what you expect if there is no relationship between race of the defendant and death penalty verdict. Yes?
Sorry, when you say there's no relationship, it means that they're dependent or independent?
Independent.
Okay.
Yeah, independent. That is our null hypothesis. We have a new degrees of freedom that we have to learn to calculate from this rows by columns contingency table. And the degrees of freedom here are the number. One way to think of it is the number of times that we have to do that initial calculation of proportion times counts before we can fill the rest in just by making sure that the row and column sums add up. And that turns out to be the number of rows minus 1 times the number of columns minus 1. So in this case of a 2 by 2 table, 2 minus 1 times 2 minus 1, that's 1 degree of freedom. And that corresponds to the fact that once you fill in one of those values, whatever you fill in one of those corners to be, then the rest are determined just by requiring the rows and the columns to add up. So that very first one is done under an assumption of independence in this case. You could put in some other value there if your assumption wasn't independence, but then the rest of them would just be filled in based on the number, making the margin totals add up. So yeah, you could do the same calculation, but it's easier just now to go 4909 minus 177.5 to get the number of no's here, and 364 minus 177.5 to get bottom left corner. And the same thing here. We fill this in with all the expected counts. So In the chi-squared test, the first step of calculating chi-squared value is this calculating the expected number of counts in each cell so that, or under the assumption of our null hypothesis of independence between the variables. Then all the chi-squared statistic is just the actual observed counts minus those expected counts that we calculated, the square of them and divided by the expected counts, added up over every cell. So observed minus expected squared divided by expected and added up. For 2x2 tables, there is this so-called Yates correction, just a bit of an annoyance correction because it makes it more nearly chi-squared distributed. What makes this test convenient is that under the null hypothesis of no dependence between the variables, this value is approximately chi-squared distributed. So if you were to repeat that sample over and over again, then this test statistic would follow what we call a chi-square distribution with this rows -1 times columns -1 degrees of freedom. And it's just like the other the distributions that you've learned, except it is a little bit different. The ones you've learned so far have been symmetric around 0, z, t. This one's not symmetric around 0. It's strictly positive, right? Because the numerator was a square. The observed are always, or the expected on the denominator. It's all positive. So chi-squared is only positive. And the further a departure we have from the expected, the smaller that probability becomes. But for any given degrees of freedom, you can look up, this is from the one of the tables in the appendix of your textbook, you can look up the critical values for 0.05% upper tail probability. So 0.995, this means the area to the left of this probability. So here, let's see if I can make this a little bigger. Is that what you're going to ask?
Yeah.
Okay.
Can you repeat what you said?
Yeah.
The further from the expected, the bigger the probability.
So let's look at one degree of freedom here. We don't have any values here. The first one we have, let's look at 0.95. So that tells me that, so these are upper tail areas of 0.95. So sorry, this is area to the right of this value, 0.004 is equal to 0.95. That's not actually what we're going to use. That's somewhere down here. What we're really interested in is an upper tail area of 0.05, which is a chi-squared value of 3.841. So what that means is under the null hypothesis, so there's no independence between the row and the column variables. Under repeated sampling, if we calculate chi-squared each time, then 5% of the time we're going to get a chi-squared value in a 2x2 table of more than 3.841. So that means that if we've selected an alpha of 0.05, we have a 2x2 table. If we get a chi-squared value of 4, we're going to reject the null hypothesis at an alpha of 0.05.
Just to make sure that value is the x squared that we get from the equation, we don't need to take the square root, right?
Right, that's chi-squared. Yeah, you don't need to take the square root. Just, yeah, traditional, I guess, that you use the squared value. So one of the things that we've noticed here is that although this distribution, it has two tails, a left tail and a right tail, we're only really interested in this probability in the right tail. So that is, these are large departures from the expected values. If you happened to have observed values that were exactly equal to your expected value, that would be a chi-squared of 0. And that's also improbable. As you see here, so the left tail probability, so the probability of having a chi-squared value of less than 0.001, that's only probability of 2.5%. So that is also improbable, but that would represent the two variables being more closely aligned than you expect by chance, even if they're truly independent variables. As a side note, what would you think of that if you saw a paper that found here, so a 2x2 table that got a chi-squared value of like 0.0001? Or let's say they didn't even report a chi-squared value, but you were reproducing it going back and you saw that the chi-squared value was 0.0001. What would you think? Something where this left tail probability was very small. Yep.
That was biased in the sample.
That it was biased in the sample? What kind of bias?
Action bias, that you sort of picked your groups in a way that they align.
The thing is generally, like, if you had selection bias for one of your groups, it's hard for me to imagine how that would make your observed and expected values become more similar.
For example, if we had a case control study,
yeah,
with paired, how is it called? You sort of pick your control, looking at the case to make them as similar as possible for demographics and whatever else to avoid
that's fine, yeah,
certain values. But maybe if you go too far, they just become too similar that there's variation.
Well, let's suppose you have very well matched cases and controls. Then
they were truly independent. There's no
so they're truly independent with your disease outcome. So okay, so if they're truly if they are truly independent,
and very closely matched, then they might be very similar.
Truly independent and very closely matched. I don't know, what do you mean by matched? Do you mean like you actually have the same people?
Well,
I mean, you can't have the same people in cases and controls.
Well, let's assume that the exposure actually has no impact at all on the disease outcome, but you look at twins. Because you want to have a very close match. There might be all the other factors shaping that outcome might be very similar.
So, but if they had no,
Just,
if there was no effect,
And
and
the exposure, which is the only thing where they differ.
yeah, so
Doesn't
that
make a
would give you a
difference.
large chi-squared, because you would actually be having, then say every twin pair would have the same exposure.
Well,
that case.
no, you look at only, you have a case control study, you look at people with cases, you're only interested in the ones that have twins.
Mm-hmm.
And so you recruit those as well,
Mm-hmm.
but the exposure actually doesn't make a difference. But all the other
Yeah.
variables are pretty much the same.
Yeah. So so there's no relationship between exposure and disease, but your twin pairs in which one has the disease and one does not have the same exposure. They're either both exposed or they're both not exposed.
No.
No.
The exposure is different between them, but everything else is the same.
But
You have one maybe is exposed and maybe the other one is not.
Exactly.
okay. So then exposure is independent. So you're saying that the fact that
There's
They're
very
twins
similar,
does not-
maybe causes selection bias? Or where would that
Well,
be?
in that case, it could happen that you get a really close chi-square.
I don't see, so let's
I
see.
think so.
Let's see. So how does that give you? We've
They're
got.
basically the same.
I need to. Okay, I can't write on the board, so I'm gonna open up an Excel spreadsheet here to write this down to talk it through. Where is Excel? There's Publisher, but where's Excel? Okay, so we've got disease, and this is case control. So let's say it's this is yes, no. So we've got, let's say, 25, 25, and so that's the, actually I should put this here. That's no, and then we've got exposure. Oh, this one, no, yes. 25, 25, like this. So this is a case where we have case control, equal number of diseases, and we happen to have and it's independent with the exposures. So these are expected counts, 25 in each cell. But these are 100 different people. So first of all, it's pretty lucky that that since we did not select on exposure, we selected on disease. It's quite a coincidence that we happen to get exactly 25 exposed and unexposed. And then this part, so here are the F4 plus G4. So this part was determined by the design, but this part was not. So how would the fact that your cases and controls are well matched, how would that help you to get exactly even numbers of exposures to not exposed?
But the other one. But yeah, I see that how that would
be.
For the sort of the disease count, it might make them very close, align them very close, but I exposure would.
You could even make it like simpler, like it's saying we've only got, we've only got 16 people in the study. And so I've gone and selected, 4 cases and 4 controls. There's somewhat there's somewhat greater probability of having the exact matched observed values now. But if I were, so we actually have 8 students in the class now, and let's say this is for something with an exposure rate of 50%, the chances of, over, as you're sampling, no matter how you're doing that, with a disease with 50% prevalence in both populations, the odds of getting exactly 4 exposed and 4 unexposed people every time is low. Like, the only case that I can think of where that's going to happen with a greater probability than you expect from the chi-square distribution is either some flaw in the sampling where you are actually selecting on both the disease and the exposure, or research misconduct. And it has actually come up in that case as well, where a researcher is throwing away cases that don't match the expectation. They expect there to be independence between these values, and so somehow some of the labels change to make it match more closely. People get dropped from the study if they didn't match, and you end up with such a close match between observation and expected that it's closer than you expect by chance. So, yeah, the lesson of that story when it has come up is it is very difficult to fake realistic data. There are so many ways you can get caught doing it. If it's something that people are interested in and you will have savvy people going up and following on your results, there are a lot of ways that artificially created data ends up looking artificial. This is one of them. So if the rows and columns are independent, then the chi-squared value is small, but not too small. If it's very large, then if it exceeds our critical value, we're going to reject the null hypothesis that those columns and rows are independent, and that the difference is just due to sampling. And in this test, the alternative hypothesis is inherently two-sided. By that I mean departures from what we expect in any direction, like a positive relationship between the 2 variables, or a negative. Whichever direction it is in will equally cause a rejection of the null hypothesis, but we only use the right tail of the distribution. We don't double it like we did with the t distribution and the z distribution, because both of those departures result in larger chi-square values. So our assumptions, first, that each observation is independent. Of course, that the sample is representative of the population. It is based on an assumption of large sample size and the central limit theorem, and as a rule of thumb, that no table in the, or no cell in the table has an expected number of counts fewer than 1, and no more than about a fifth of them have expected counts less than 5. It's an approximate rule of thumb. For small samples, an alternative is the exact binomial test. I'll mention another one that ends up getting used in this situation incorrectly, in my view. That is the Fisher's exact test. But no assumptions about the population distribution are required because it's just a categorical variable. It's not like continuous variables where we have to make distributions about that distribution, or assumptions about that distribution of a continuous variable. So let's go ahead and do it for this data set. Down here were the expected counts, the observed counts. The chi-squared statistic is 39. Remember, the critical value is about 3.8. So it's much, much bigger than we expect under independence. And the exact p-value is quite small. So we reject the null hypothesis and have to consider that there is evidence of a relationship between death penalty and the race of the defendant in Florida. So where does, we reject the null hypothesis, and then we want clearly to ask, where is that association coming from? So one way we can do that is by calculating the proportion of death penalty verdicts. Among white defendants, it's about 4.8%, and among black defendants, it's only about 2.5%. But it turns out there is more to it than this. So overall, the white defendants had almost twice as high a probability of receiving the death penalty than the black defendants. But so in this paper, they look into it quite a bit more, and additionally do an analysis conditionally on race of the defendant. So not just so this is the calculation that we just did. So we'll get in a minute to the analysis by race of the victim. So that calculation I did on the previous page, this was proportion of death penalty verdicts conditional on race of the defendant. This is called a risk ratio if you just divide those two things. So the probability of death penalty conditional on the defendant being white divided by probability of the death penalty conditional on defendant's race being black is about 1.94, and that is a risk ratio. The second way that we can describe this difference in probability is with an odds ratio. So odds ratio is more complicated to calculate rather than just the ratio of probabilities. It's a ratio of probability over 1 minus probability. This is the odds. So there's a fair bit more calculation to go into here, but it comes out fairly similar, 1.98 instead of 1.94. So instead of just 0.048 on the numerator, it's 0.048 over 1 minus 0.048 for the odds ratio. The difference between these two matters. In this case, it doesn't make too big of a difference, but one of the instances where your choice, one is easier than the other, is that for odds ratios, there are a couple of different ways you can calculate it. One is using, so going back to disease and exposure notation, using the probability of disease given exposure and given non-exposure. But the second way is reversed, so probability of exposure given disease. Whereas with risk ratio, there's only one way to do it. That is probability of disease given exposure. So you have more options for calculating the odds ratio. It's not immediately obvious why these are both equivalent. It involves going through a bunch of algebra with the Bayes' theorem, and you remember these two things, like probability of disease given exposed is related to probability of exposure given disease through Bayes' theorem. And if you were to plug in Bayes' theorem here to a bunch of algebra, you would find that it is exactly equivalent to this second calculation. So both of these can be calculated for a cohort study. That is one where we have a random sampling from the population, where we're not conditioning our sampling on exposure or disease. We're just randomly selecting from the population. But in a case control study, we're selecting conditionally on whether they have the disease or not. So we select a certain number with the disease, a certain number without the disease. Or in statistician language, the selection is conditioned on disease status. And in that case, we can still calculate the odds ratio with that second formula, but this probability of disease given exposure, we can't calculate from a case control study, because this probability of disease is getting fixed in the case control study. So we can't calculate it because we've designed it that way. So in the case control study, you can calculate odds ratio, but you can't calculate risk ratio unless you know the prevalence and you go through some Bayes' theorem calculations. But just from your data, you cannot calculate it. For rare events, they're almost identical. For common events, they're more different. So for winning a lottery, they're basically the same. It's 1 in a million versus 1 over 999, 999. Whereas for something like a dice, it's 1 over 6 compared to 1 over 5, and they get more of a difference there is. Statistics, we usually use odds ratio for this reason and other conveniences. When you learn logistic regression, the coefficients can be interpreted directly as a log odds ratio. So it's convenient, even though it's a little bit less intuitive. So let's go ahead and calculate more of these odds ratios here, but we're now calculating them by the victim's race. So we're calculating the same odds ratio. This is, an odds ratio according to the race of the defendant, but we're doing it separately here just for white victims. So for white victims, this odds ratio, so the odds of death penalty, given that the defendant is white, is less than 1. So for white defendants, or for white victims, the white defendants are less likely to be given the death penalty. Whereas for black victims, then white defendants are more likely to be given the death penalty. And going through and doing that with all of the possible permutations of victims, we find that, in fact, the cases that are by far the most likely to result in the death penalty are a black defendant and a white victim. So I don't get into it more than that, but it's a pretty interesting study. And then obviously this is an observational study. You can't say just from the data itself what is going on here, but there's a lot of sort of knowledge of those cases and of the political environment around race and juries in Florida that's required to understand
1991.
what is going here. And yeah, the paper, so the ages of the study was from like 70, I
think it was, right?
to 88 or something like that. So yeah, I would be interested to see if this data has been updated since 1991. I'll take a look. So what's very clear here is that they're not independent. The death penalty and either the victim's race or the defendant's race. And also it's not independent, the race of the victim and the race of the killer. In most cases, it is white suspects killing white victims and black suspects killing black victims. And in the few cases that are not like that, result in higher rate of the death sentence. And for those suspected of killing blacks, is rarely the death sentence. And like I said, this is an observational study. We can't make causal conclusions from the data. We can't determine what is different about those cases or how the jury are applying the death penalty. But we can, for these data, clearly rule out independence. And we can identify what we call a statistical interaction there, in that there is not only a relationship between race of the defendant and race of the victim and the death penalty, but there's an interaction between race of both the defendant and victim and the death penalty. So a few related tests. For paired samples, you can use McNemar's test, and for small samples, you can use an exact binomial test. There is a third test which comes up pretty frequently in the literature, Fisher's exact test, which is often gets applied as a replacement for the chi-squared test for small samples, but I observe it being applied in a lot of cases where the null hypothesis doesn't actually match the study, because the p-value calculated is under the assumption that the marginal totals of your table are fixed in the design of the experiment. And the paper where R.A. Fisher introduced it, he actually gave this example as a nice memorable example of when Fisher's exact test is intended to be applied. And in the example, a British lady is given 10 cups of tea, where 5 have had milk added before the tea and 5 have had milk added after the tea. And this lady claims to be able to tell which ones tell when the tea has been added before or after the milk. So in this study, she correctly identifies all 10, and then the question is, okay, what is the probability of this under the null hypothesis that she is simply guessing? And in this case, it turns out that it's improbable that with an alpha of 0.05, we have to reject that null hypothesis. But you notice that she is told that 5 have milk added before and 5 have milk added after. So if she's smart, which she is going to make sure that her guesses match that, so that she guesses 5 with milk before and 5 with milk added after. She's not going to guess 9 and 1 or 10 and 0. So if she were not told that that design, so that 5 were before and 5 after, and she knows that, then this p-value is going to be incorrect. You know, if you could imagine doing a different one where you just, before each cup of tea, flip a coin and decide whether or not to add milk before or after, then there's no guarantee that it's 5 and 5, and she's not necessarily going to guess 5 and 5. So that is more of a chi-square distribution type of situation. Margins are not fixed by design, but you'll see Fisher's exact test applied over and over in cases where these marginal totals are not fixed. I don't do it, and I tell people to change it when they do that, but it appears a lot in the literature. So we have methods now for hypothesis testing for 2 categorical variables. If they're both binary variables, you can also calculate the risk ratio and the odds ratio. Under these tests, the null hypothesis is independence between those 2 variables. And these tests, they're two-sided, even though we use only the right tail of this chi-square distribution. And of course, you remember your type 1 and type 2 errors. Any questions before we hurry for time? Perfect timing. Yes?
Would you use this test also if you wanted to detect changes in proportions between 2 time points?
No. So a change in proportions between 2 time points, like let's say, I mean, this kind of reminds me of, what example have we done? Like let's say an approval rating now and in a year from now. That is just 2 proportions. You would do it if you wanted to say whether trying to think of an example with 2 time points where you might use this. I guess if your observations were paired across the time points, like you know, an individual giving their approval or not now and saying whether they approve of a politician now and in another year from now, and your null hypothesis is that there's no change over the time points. That could be potentially a paired samples kind of design. All right, let's take a quick break and start up again at 6:10.